This is a walkthrough of Problem 3 from Practice Exam 2 in Module 4 from the book Problem Solving Guide for Mechanics and Thermodynamics. A curved exit ramp has a radius of 40 meters, that's a tight curve, is banked inward at 10 degrees. A 1,000 kilogram car is negotiating the curve at a constant speed of 25 meters per second, which is too fast. What is the magnitude of the frictional force on the car from the surface of the road? Let's start with a good diagram. There's our 10-degree curve. The car is coming straight at you. Let's identify the forces. We have gravity. That's an easy one. We have the normal force, which is normal to the surface, perpendicular to the surface, and the frictional force, which is along the surface. Now we have to pick a coordinate system. The acceleration is towards the middle of the circle. The car is moving in a horizontal circle. The acceleration is towards the middle of that circle. The acceleration is directly to the left. If we put the x direction there, then a sub x is v squared over r, and a sub y is 0. So that's what we're going to do. There's our coordinate system. Now we're going to treat the car as a point mass and get the angles each vector makes. With the coordinate system, we're going to get rid of the car. So that's what it looks like. The 10 degrees angles are here and here. Now we're going to do F equals ma in the y direction and F equals ma in the x direction. In the y direction, F normal cosine 10 degrees, that's this vector right here. That has to balance frictional force sine 10 degrees and gravity. The upward forces balance the downward forces. Fn cosine theta, cosine 10 degrees, balances Fr sine 10 degrees and mg. We can put in the numbers for sine and cosine of 10 degrees and we get that. We can put in mg. M is 1,000. G is 10 newtons per kilogram. That's all we can do with that. In the x direction, there is acceleration. And it's produced by the normal force, sine 10 degrees, this part right here, and the frictional force, cosine 10 degrees. There's two inward forces, and they are equal to ma. And because we chose our x-axis horizontal, we can plug in v squared over r for a sub x. We have m and v and r. We can plug those in and get the acceleration, get the net force, 15,625 newtons towards the middle of the circle. And those are the forces. So now we have two equations and two unknowns. In the vertical direction, we balance the forces. The upward force equals the downward force. In the x direction, we have the sum of the forces is ma sub x. So we just have to solve this, and there's a number of ways to do it. We can use the horizontal direction, solve for Fn, subtract this from both sides, divide by 0.1736, and then simplify. We get 89,980 newtons minus 5.73 F sub r. We can stick this into the vertical direction. Just a bunch of math. And we get this. Distribute the 0.9848 and collect the FR terms and then solve for frictional force. We get 13,650 newtons. So, safety tip. Do not take 40-meter curves at 25 meters per second unless the curve is banked inward at a lot more than 10 degrees. Let's not leave it here. Let's calculate the magnitude of the normal force. There's the equation for the normal force. We have the frictional force now. We can plug it in, and we get 12,600 newtons. So let's head to tail the three forces. Using two scale vectors, we're going to make them all the right length. So here's our coordinate system. The normal force is 12,600 newtons, and it's 10 degrees to the left of the vertical axis. There it is, 12,600 newtons. Next, we have the frictional force, 13,650 newtons, a little bit longer, and it's 10 degrees downward, which is a right angle to the normal force, of course. There we go. Now we have gravity. Gravity is straight down, and the magnitude is 10,000 newtons. The sum of these three vectors is the net force. And if we draw, the net force is 15,625 newtons, and if we put that in, there it is. There's the net force. It's directly inwards towards the middle of the circle, and it's producing the acceleration, ma, which is mv squared over r. That's problem 3.